Today's laboratory work number 1. Determination of the rigidity of LS. Write down to your notes the name of our laboratory work, the purpose of the work, and equipment, instruments, and accessories. The purpose of the work is to study and master methods for determining the rigidity of metal cutting machines, or less, to determine the rigidity of a 1M61 screw cutting less under cutting conditions and under static load. It was purpose of the work and equipment, instruments, and accessories. First is screw cutting less 1M61. Then center mandrel for testing the machine for rigidity. Third, rotating workpiece ring for fourth, rear center. Through hole cutter with T15K10 insert. It's material of cutter. Indicator head and a set of weights. So write down to your notes the name, the theme of our laboratory work, the purpose of the work, and equipment, instruments, and accessories. Content of work and order of execution. The production method for determining the rigidity of the machine is based on the principle of processing workpieces with an uneven allowance variable depth of cut. An uneven allowance during processing is obtained in laboratory work due to the eccentricity of the workpiece. When processing an eccentric workpiece, the depth of cut per revolution of the workpiece changes from T maximum to T minimum, which causes a corresponding change in the cutting force and accordingly the elastic movements of the technological system. So in the next slide you can see the general view of the screw cutting lathe machine. Processing of the external surfaces of the workpiece on a screw cutting lathe. You can see a workpiece. You can see the chuck, support, and another part of the lathe. One more workpiece and one more workpiece is a cutter. And let's see next slide. In this slide, you can see the lathe machine. The main parts of the lathe machine, it's tray, two legs, feed box, Headstock assembly, tailstock assembly, that on the tray. We have a mandrel gear and pulley system, and support. And we have the support hand traveling wheel. Tool post to take the cutter. You can see the spindle and chuck. And you can see the workpiece. Now let's see the video about our lathe machine. First video for today.
Welcome to Academic Game Tutorial from the workpiece to give it a desired shape.
Construction, details and operation of lathe machine.
And size. So, the function of lathe is to remove the metal from a workpiece in the form of chips by mounting the workpiece rigidly on a machine spindle and revolving at the required speed, and the cutting tool is fed against the work either longitudinally or crosswise to make the work to the required shape and size. Now, let's look at the construction details of a lathe machine and the operation of different parts that together construct a lathe machine. First of all, we have the stands, or legs, in a lathe machine. This is used in holding the lathe machine and then elevating the lathe bed to a working height. Legs are the most bottom portion and carrying the entire load of a lathe machine tool. The legs are firmly secured to the floor by the foundation bolt. The legs or stand of lathe machine is made of cast iron through the casting process. Since cast iron has a high shock absorbance and wear resistance capacity, so it helps the legs to absorb the vibration during work and transfer to the ground. Above the legs, there is a tray. This is also known as chip span. It is placed at the lower side of bed and above the leg of lathe machine. The main function of chip span or tray is to collect or carry all hot chips removed from the workpiece during machining operation. Above the tray, there is the bed of the lathe machine. It is also called the lathe bed. The bed of a lathe machine is the base on which all other parts of lathe are mounted. It is massive and rigid single-piece casting made to support other active parts of lathe machine. The bed is chosen according to lathe machine specification and requirement. It is usually made by single-piece casting of semi-steel or chilled cast iron due to its high compressive strength, shock absorbance and high lubrication quality. If we are making a larger lathe machine, then 2 or 3 pieces of the bed are casted and then bolted together. And for comparatively smaller general-purpose lathes, the lathe bed is made through single-piece casting at a time. There are guideways on the lathe bed. These guideways take care of movement of tailstock and carriage on bed. On the bed, there is the feed box. This feed box is connected to the lead screw and the feed rod. The lead screw is an externally threaded shaft or rod. It converts rotational motion to linear motion. Lead screw is used for thread cutting operation in a lathe machine tool. The lead screw is used to move the carriage automatically during thread cutting. The feed rod is a cylindrical rod. It does not have any thread on its external surface. This feed rod is used to move the carriage from the left side to the right side and also from the right side to the left side. Now, on left end of the bed, headstock of lathe machine is located while on right side tailstock is located. Headstock is situated at the left side of the lathe bed and it is the house of the driving mechanism and electrical mechanism of a lathe machine tool. Headstock transmit power from the spindle to the feed rod, lead screw and thread cutting mechanism. There are speed selectors for controlling gear speed. And here, we have a lever called the driving clutch, which is used to engage and disengage the spindle from the gear mechanism inside the headstock. In other words, it engages and disengages the motion. At the starting of the lathe, this driving clutch keeps the motion disengaged from the spindle, and then when we need we can use this clutch to engage the spindle with gears for motion, and the spindle starts rotating. Here this is the spindle connected to the headstock. The spindle possesses live center to which the workpiece can be attached. There is a hole throughout spindle for handling long bar of workpiece. The spindle is hollow inside, and has threads cut on the external surface. On the other hand, the chuck has threads cut on the internal diameter. So, the external thread on the spindle surface and internal thread of the chuck results in coupling or fitting of the chuck with the spindle, just like nut and bolt. After mounting properly, the chuck and the spindle becomes an assembly. The chuck here is used to hold the job or workpiece firmly during the machining operation. As we have just discussed, it is mounted on the spindle which rotates the chuck and workpiece. Depending on requirements, we usually use two types of chuck, 3-jaw chuck and 4-jaw chuck. The 3-jaw chuck is also called universal chuck because the 3 jaws move simultaneously when any one jaw is adjusted. These 3-jaw chucks are generally used to hold cylindrical jobs. The 4-jaw chuck is also called independent chuck because in 4-jaw chuck each stepped jaw is independently operated by a different screw. So, the 4-jaw chucks can also hold the square jobs rather than cylindrical. The tailstock is situated on the right side above the lathe bed. It is made out of cast iron. The tailstock moves on the guideways on the bed surface, and it can be moved forward and backward, towards and away from the chuck according to requirement and job length. The tailstock is used for supporting the long end of the job for holding and minimizes its vibration and sagging, so that the long workpiece or long job does not deflect or bend during the machining operation. It holds the tool for performing different operations like drilling, reaming, tapping, etc., and it is also used for a small amount of taper for a long job by offsetting the tailstock. This tip portion of the tailstock is also called the dead center because it just provides support, and no motion is provided to this point. Similarly, on this side, we provide motion to the spindle, which in turn rotates the chuck and workpiece, so this is called live center. Both live and dead centers have 60 degrees conical points to fit center holes in the circular job, the other end tapering to allow for good fitting into the spindles. The dead center can be mounted in ball bearing so that it rotates with the job, avoiding friction of the job with dead center as it is important to hold heavy jobs. In the tailstock assembly, we also have the ram clamp and the hand wheel. When we rotate this hand traversing wheel, this dead center moves back and forth. That is, when this hand wheel is rotated, the dead center moves in and out. The ram clamp is used to apply lock on this movement of dead center. So this ram clamp locks the dead center in the tailstock, so it does not move. In addition to this, there is also a tailstock lock, which is used for locking the tailstock firmly in place according to our requirement during machining operation. On the left of the headstock, there is the main driving pulley and gear system. This driving pulley system is connected to the gearbox inside the headstock. This driving pulley is connected to the motor through belt. Then comes the carriage. The carriage is used for support, guide and feed the tool against the job when the machining is done. The carriage holds, moves and controls the cutting tool. It gives rigid supports to the tool during operations. It transfers power from feed rod to cutting tool through apron mechanism for longitudinal cross-feeding. Carriage simplifies the thread cutting operation with the help of lead screw and half nut mechanism. The carriage is formed of 5 parts: saddle, cross slide, compound rest, tool post, and apron. On the carriage there is a hand traversing wheel. Using this wheel we can move the carriage left or right along the feed rod and lead screw. There is a half nut or screw cutting engage lever on the carriage. This half nut is used to connect motion to the carriage automatically. If the half nut lever is engaged, it engages the carriage with the lead screw, which results in automatic movement of carriage right and left by being guided by the threaded lead screw. Thus, the split half nut is used for automatic feed instead of providing manual feed, which helps us to cut thread with accuracy. Mounted on the carriage there is a saddle. Generally, the saddle is made up of H-shaped casting and it has a V-guide and a flat guide for mounting it on the lathe bed guideways. The cross-slide hand wheel is assembled on the saddle. The cross-slide generally travels at right angles to the spindle axis. That is, let's take for reference, if this hand-traversing wheel moves the carriage left and right, then this cross-slide wheel moves the saddle towards front and back, that is perpendicular to the bed. So, since the cross-slide hand wheel gives cross movement or perpendicular movement, so it is called cross-slide. Above this cross-slide and saddle, there are compound rest mounted above them. The compound rest supports the tool post and cutting tool in its various positions. It can be swiveled at any desired position in the horizontal plane. Compound rest is necessary for turning angles and boring short tapers. It can rotate and fix to any desired angle. The compound rest slide is actuated by a screw, which rotates in a nut fixed to the saddle. Then, above the compound rest, the tool post is mounted. The tool post is an important part of carriage, which fits in a T-slot in the compound rest and holds the tool holder in place by the tool post screw. It is the topmost portion of the carriage and it is used to hold various cutting tools or tool holders. Generally, the single-point cutting tool is mounted on this tool post. The last part of the carriage is the apron. This whole portion is called the apron. The apron is fitted to the saddle. It contains gears and clutches to transmit motion from the feed rod to the carriage, and the half nut which engages with the lead screw during cutting threads. Apron acts as a cover or housing for all the mechanisms inside the carriage. Below the lathe bed, there is an oil sump. This oil sump is a place where the machine oil from different parts, especially the machine oil from the shaft, is deposited in the oil sump. In the bottom portion on the leg of the lathe machine, there is also space which can be used as storage for gears, chucks, tools, etc. And also this space is used as a housing for motor mechanism in some lathe machine. So, we have learnt the construction details of a lathe machine, along with the detailed operation of different parts.
So it was the lathe machine and different parts of lathe machine. The magnitude of the elastic displacement of the system, Y suffix S, when processing a part on a lathe depends on the displacements of the nodes Y suffix M of the machine, the cutting tool Y suffix T, and the workpiece Y suffix W. So we have the formula 1.1. Y suffix S is equal Y suffix M plus Y suffix T and plus Y suffix W. Y suffix S, the magnitude of the elastic displacement of the system. Y suffix M, displacements of the nodes of the machine. Y suffix T, displacements of the nodes of the cutting tool. And Y suffix W, displacements of the nodes of the workpiece. Then the rigidity of the system. We use the formula 1.2. One divided by J suffix S is equal the sum of these parameters. J suffix M and J suffix T and J suffix W. Since the
And what is teacher J suffix M, J suffix T, J suffix W?
J it's rigidity,
Oh
and
yeah.
rigidity S it's rigidity of the elastic displacement of the system. It's rigidity of the system. J suffix S. J suffix M it's rigidity of the nodes of the machine. Use suffix M2. J suffix T, like in this formula, suffix T, its rigidity of the nodes of the cutting tool. And J suffix W is rigidity of the nodes of the workpiece, rigidity of the workpiece. Since the rigidity of the tool in the radial directions is much greater compared to the rigidity of the machine and the workpiece, its deformation can be ignored in the calculation. So, if we ignore the deformation, then we have a new formula, 1.3. Only we use J suffix M. In previous slide, we don't use J suffix T and J suffix W. So, in addition, the deformation of the workpiece can be eliminated. The rigidity of the workpiece is much higher than the rigidity of the machine. Then we use formula 1.3. The rigidity of the machine when using the production method is equal to, we use formula 1.4, the rigidity of the machine, J suffix M, is equal P suffix Y divided by Y. P suffix Y, it's the force, and Y, it's deformation. The normal component, let's see in previous slide what is Y. Y, it's displacement of the system, or Y suffix, it's displacement of the system. The normal component of the cutting force, P suffix Y in this formula, it's a normal component of the cutting force, is expressed in terms of the tangential component of the cutting force P suffix Z. Then P suffix Y is equal Ky multiplied by Pz. In this formula, K suffix Y is the coefficient characterizing the ratio Py by Pz. Depending on the geometry of the cutter, the state of the cutting edge of the cutter, and the mechanical properties of the material being processed. To calculate cutting force P suffix Z, we use the formula 1.4. Pz is equal C suffix P multiplied by T and multiplied by S to the power of 0.75. In this formula, in formula 1.4, C suffix P is a coefficient depending on the mechanical properties of the material being machined and the cutting angle. T is cutting depth. S, it's feed. Let's look at the previous slide. You see the carriage and it can be moved right and left. And the movement of carriage, it's a feet. Movement of carriage right, or move carriage to the left, it's a feet. Speed of move, it's a feet. S, feet. Then we use the formula 1.5. We know p suffix z, and we know that p suffix y is equal k suffix y multiplied by pz. So k suffix y multiplied by pz, it's c suffix p multiplied by s to the power of 0.75. And we use then, we have displacement calculated by the formula 1.6. J suffix m, it's rigidity of material, of the part. When machining an eccentric workpiece is one pass, the depth of cut changes from T suffix minimum to T maximum, and accordingly, the change in the depth of cut changes to the deformation from Y minimum to Y maximum. Then the difference Y is equal Y maximum minus Y minimum, and we use the formula 1.7, 1 divided by rigidity of materials multiplied by K suffix Y multiplied by C suffix P and multiplied by S to the power of 0.75 and multiplied by T, difference between T maximum and T minimum. In this formula, Y suffix maximum minus Y suffix minimum is equal delta P. It's delta of path run out, path shape error in millimeters. And T maximum minus T minimum. T maximum minus T minimum is equal delta W, delta of workpiece. Workpiece run out or workpiece error in millimeters too. Delta P is determined by the formula 1.8. We use delta P and delta W in the formula 1.7, and we have formula 1.8. Or if we must find J suffix M, then we have formula 1.9. J suffix M is equal K suffix Y multiplied by C suffix P multiplied by S to the power of 0.75 and multiplied by delta W divided by delta P. The ratio delta suffix W path, it's workpiece error divided by delta P path shape error. The ratio is called the refinement of E. So we use E and then we have the formula 1.10. So the rigidity is equal K suffix Y multiplied by C suffix P multiplied by S to the power of 0.75 multiplied by E. In this slide, you can see The mandrel with workpiece rings. This mandrel is like a workpiece on the lathe. We use 3 rings, 1, 2, and 4, 1 ring, 2 ring, and 4 ring. Third ring, number 4 in this figure. So first ring, it's ring at the headstock of the machine. Second ring, ring at the middle of the mandrel. And third ring, number 4, ring at the tailstock of the machine. Let's see where on the machine headstock and tailstock. Headstock, there are headstock and there are tailstock of the machine. And we use the mandrel between headstock and no, we use the mandrel like a workpiece between headstock and tailstock. In figure 2, you can see workpiece and its installation on the machine. It's headstock and tailstock. There are headstock and tailstock. Ring at the headstock of the machine, ring at the middle of the mandrel, and ring at the tailstock of the machine. You can see in this figure the T suffix 1 and T suffix 2. It's T maximum and T minimum. It's depth of cut. Depth of cut. In figure 3, you can see the mandrel dimension after tuning. And we have delta T, T maximum minus T minimum on the ring at the headstock of the machine. Delta T suffix 2, it's on the ring in the middle of the mandrel, and delta T suffix 3 on the ring at the tailstock of the machine. Thus determining the rigidity of a lathe by the production method, by machining an eccentric workpiece. In previous slides, you can see the ring. They have eccentricity. All 3 rings have the eccentricity. So is practically reduced to measuring the runout of the workpiece before and after processing. We determine the eccentricity before and after processing. It's delta P and delta P and delta W. It's workpiece error delta W and delta P path error after processing. The feed and cutting speed during measurements should be taken such that after tuning, a clean surface is obtained, providing a more accurate measurement of the runout. To determine the rigidity of the lathe in a production way, a special mandrel is used. Special mandrel you can see on figure 1. It's special mandrel with 3 rings. All rings have eccentricity. The first ring of the mandrel is used to determine the total rigidity of the headstock and caliper. The second ring is the total rigidity of the machine, and the third ring is the total stiffness of the caliper and tailstock. The rings are mounted on the mandrel and fixed with a nut. The distance between the rings is regulated by bushings. When removing the eccentric allowance, it is advisable to perform processing in one pass up to the middle of the ring width. On the obtained longitudinal profile of the ring, the measurement of the runout of unmachined surface will determine the error of the workpiece delta suffix W. It's error of workpiece, and of the machining one, the error of the part delta suffix P. If we will know the delta W and delta P, then we can use the formula delta W and delta P we know, then we can use the formula 1.9 and determine the rigidity of machine, J suffix M. So now before we start to calculate the rigidity of the lathe, you need to see another video.
Okay.
Another video with the process, with this method. It's a lathe. We use the mandrel with 3 rings. We load mandrel to the chuck. Its parameters of the cutting process. We have 3 rings. The ring at the headstock of the machine, the ring in the middle of the mandrel, and the ring at the tailstock of the machine. It's a tailstock at the machine. And now we start machining. All 3 rings have eccentricity. It's our tables, table 1. We start process. and start cutting. We use a cutter. Third ring, middle ring, and first ring will be processing. And after the cutting, we must determine the error delta P, delta of part after cutting, and delta workpiece before cutting on all three rings. So we have delta before cutting, delta of workpiece, and delta P, it's delta after cutting. Use the parameters from this slide. The value of delta workpiece and the values of delta P from this table. Ring at the headstock of the machine, delta W is equal 1.53, after processing 0.6. On the ring in the middle of the mandrel, delta of workpiece is equal 1.45, and after processing, delta suffix P is equal 0.7. Ring at the tailstock of the machine before processing, delta of workpiece is equal 1.15. After processing, delta P is equal 0.92. Then you use the formula to calculate clarification E. E is calculate by the formula on the slide. E is equal delta suffix W divided by delta P. Then, if you know E, you can calculate the rigidity, G suffix M. Use the formula 1.9. Use the coefficient K suffix Y is equal 0.9 and C suffix P is equal to 4, 3. And S 0.1. Please calculate E and J, M, and write down the results to the table 1.1. Okay, when you finish the table 1.1 and 1.2, choose
Результаты поиска.
excuse me, what you need to have in your report. First, name of practical role. Second, enter the measurement results in table 1.1 and table 1.2. Calculate the rigidity values according to the production method and Boole graph of the static loading method. Calculate the rigidity value. You have all these items. So please finished your practical, your laboratory work. Write down the
name of the practical works and my name too.
yes. Make a conclusion, and when you finished your report, please send it me into the Telegram group.
Okay, teacher. I will send it to you. I can send it tonight